Hello and welcome back. Today we're going to be talking about a new variable and doing a few practice problems. Shouldn't be as long of a video this time, but first we're going to have a little mini history lesson. So, as you probably have learned, back in World War I, chemical warfare became a big thing. And one of the most lethal and dangerous chemicals that was used was phosgene, which is COCl2. So this reaction here, this decomposition of phosgene, is actually reversible, which means that we can have an equilibrium. And we know that the value of K is really small. So if you think about it, if you were to write out your K formula, that means we have a lot of reactants and not very many products. So that would mean that when you have phosgene floating around in the air, sure, some of it's going to become carbon monoxide and chlorine gas. However, mostly we're going to have phosgene floating around, which means that people will be breathing it in. And what do our bodies contain? Water. So let's imagine what might happen if somebody were to breathe in phosgene and have it react with the water in their bodies. Well, we would end up with carbon monoxide, which if you have carbon monoxide in your body, then it's going to inhibit your ability to respirate or take in oxygen, so that's not good. And you will also end up with hydrochloric acid inside of you. Also not good. Hydrochloric acid is going to start burning your internal tissues. Not good. So phosgene, very, very dangerous, and it caused about 80% of the 100,000 deaths that were caused by chemical warfare. So out of the different chemicals that were used, phosgene was definitely the worst. So moving on then to a new topic, we are going to learn about Q, which is known as the reaction quotient. So we have equilibrium constants, which are K, and then we have reaction quotients, which is Q. And Q is a number obtained by substituting reactant and product concentrations or partial pressures at any point during a reaction into an equilibrium constant expression. So in other words, instead of using equilibrium concentrations, we're using concentrations from any point in the reaction. It could be right at the beginning, it could be halfway through, or it could be when it's at equilibrium. The point is, these are experimental values, and it could be at any point in the process. And when we find our Q value, we compare it to our K value, which should be known. Either it's given or calculated or found in a chart somewhere. We compare the values, and that tells us whether the reaction really is at equilibrium or what's going to happen next. So here's an example. This reaction quotient equation is based off of the generic AA plus BB reacts to form CC plus DD. So same formula as your equilibrium constant, except this time we're using the letter Q because we don't know that it's equilibrium. So there are some things you're going to want to memorize. You're going to want to know what it means when your Q is equal to K, when Q is greater than K, and when Q is less than K. And luckily for most of these you can logic your way through it if you forget this information. If Q is equal to K, the reaction is at equilibrium. That means that the concentrations that you have plugged in, or the partial pressures that you have plugged in for K, are the same concentrations that you would find at equilibrium. So they are one and the same here. If you find your Q value and it is larger than your K value, that means that at this instant in time we have too many products and not enough reactants, really small r. Too much product. It's making our value too large, and that means that we need to lose products. So if I have like reactants become products, what will happen is the reaction will shift to lose products. It will shift to the left to remove products. Shift left. It's going to shift to the left in order to eventually reach equilibrium, where your concentration of your products and reactants are more balanced out. Now, if your reaction quotient is smaller than K, so that would mean that you don't have enough products, and it's going to achieve equilibrium by trying to form more products. So if we have our generic equation of reactants turning into products, the equilibrium is going to shift to the right. We want to shift right in order to decrease our reaction concentration and increase our product concentration. That will give us a larger Q value, which will eventually hopefully equal K and be at equilibrium. So let's try actually testing this out now. We're going to do, I believe, 2 examples and then we're done. So here we have N2 plus H2 becomes NH3. Right now I'm going to say, no, I don't like that. It's not balanced. I'm going to balance it. So I'll put a 2 over here, and I'll put a 3 over here. All right, so let's move on. It is telling us our equilibrium constant. This is what we are ultimately comparing with our reaction quotient. So I don't want to lose that number. And this is what it is at 472 degrees Celsius. The temperature matters. The temperature matters. If it's a different temperature, the equilibrium constant's different. We're going to imagine that we're placing 2 moles of hydrogen, 1 mole of nitrogen, and 2 moles of ammonia at 472 degrees Celsius, same temperature, into this container. Let's also add in that it's 1 liter. The volume is going to be 1 liter, so that way we can calculate molarity. So it's asking, is the system at equilibrium? And how will the mixture react in order to reach equilibrium? So, first step, this is the answer here, but let's actually write it out. QC. Let's write out our generic equation. So we'll need to have the products over reactants. And reactants. Okay, I'm purposefully leaving stuff out. What am I missing? Hopefully you said, oh, we're missing this cubed and that needs to be squared because of our coefficients up here. All right, so I have that. Now I'm going to plug in my numbers. So since I'm assuming, or I'm telling you to assume, that we have 1 liter of solution, then all of these are going to be the same as their molarity. So this will be 2 molarity, 1 molarity, 2 molarity. So I'll plug them in now. I have 2 molarity of NH3 squared over N2. What's that? 1 molarity, and H2 is 2, but that one is squared. And, oops, I think I did something wrong here. Oh yeah, I did. My hydrogen should be cubed. All right, so this is going to come out to 1/2, which is the same thing as 0.500. Now we're going to compare this to our K value, which is 0.105. So this number that we have is larger than the equilibrium constant. It's larger. So if it is larger, that means I have too many products. Let's see, how should I say that? I'll just write too many products. So if I have too many products, I need to change that. So up here, if ammonia is my product, I need to shift away from the products. I need to shift to the left in order to increase my reactant concentration. So here it is written in different words. Reaction is going to proceed from right to left. It's proceeding to the left until equilibrium has been established, when Q finally equals K. All right, let's do our final example. At 448 degrees Celsius, the equilibrium constant, Kc, for the reaction H2 plus I2 reacts to form 2HI, is 50.5. So let me just write that. Kc equals 50.5. All right, and actually I'm going to put that somewhere a little bit less in the way. Kc is 50.5. All right, is the system at equilibrium, and predict which direction the reaction will proceed to reach equilibrium. And here are our starting, not concentrations, numbers of moles. We have to create concentrations out of this here. So I'll go ahead and do that now. Let's just write this up here. I like having it up at the top. 2HI. I'm going to write my concentrations up here. So 2 times 10 to the negative 2 divided by 2. Let's see, that is going to, you know what? Let's do this. Let's try a different strategy. Let's write my formula, my basic generic formula. So I have my products over my reactants. And yes, I'm purposefully leaving out the exponents again, so you should figure out what those are. Hopefully you put that 2 up there. Now I'm going to say, all right, I think I need my pen to be smaller. I'll have 2 times 10 to the negative 2 divided by 2 liters. That's where that's coming from. This will be squared, divided by H2. Where's H2? 1 times 10 to the negative 2, divided by 2. Now that one is not squared or anything. And then finally my iodine, which is 3 times 10 to the negative 2. Also over 2. I'm doing this because I am creating concentrations out of what they've given me. This is all moles over liters, moles over liters, moles over liters. All right, so plug this in your calculator and you end up getting QC is equal to 1.33. That's kind of a messy calculator equation, so you might want to pause it and make sure you can get the same thing as me. All right, so when I compare this to my equilibrium constant, I find out, this is smaller than 50.5. It's smaller. So think to yourself, if it is smaller, what does that mean about my concentration of reactants or products, and which way does it need to shift? So go ahead and pause it and figure that out so you can compare it to what I have. All right, hopefully you actually paused. So if I have a reaction quotient that is too small, just to help myself visualize that, it's too small. That means I have way too many reactants. So up here, I need to shift away from the reactants. I need to create more products. So it's going to shift to the right, or you could have said from left to right. That would also work. Shift to the right to create more products or have less reactants, which will eventually allow the equilibrium constant to be equal to the reaction quotient. All right, let me just make sure. Yep, that's it. That's the whole video. Yay! So make sure you bring any practice worksheets that you haven't done yet to class tomorrow with any questions that you might have. Hope you have a great rest of your day.